So finally, we can get to the problems in section 1.1. I mean, realistically, I could just lecture on how to do the problems without any theory, and it probably would be just fine, but I just kind of feel obliged for the first lecture to do a little bit more theory than I might in general. And I have problem 1 up on the screen right now. I'm going to do problem 2 as opposed to problem 1. But real quickly, each of the problems between 1 and 11, at least maybe between 1 and 10, they give me a graph of a piecewise function, and they first in parts A, B, and C want me to just find a function value, and they want me to do f of some number, and this is just going to be the y-coordinate of a point marked with a closed circle. As opposed to an open. And if the only point above that x with the x value in the parentheses, if the only point is marked with, and hardly looks like with, but it is, with an open circle, then it's going to be a DNE. So just glancing at your problem number 1, to do f of 1, I look for 1 on the x-axis. That means I can tell where 1 is on the x-axis because there's going to be points above and below it that are marked with 1. And I look, and there's 2 points that have x coordinates of 1. The point 1, 2 marked with an open circle, the point 1, 1 marked with a closed circle. I'm looking for the point 1, 1 because it's marked with a closed circle. It's the y-coordinate of the point marked with a closed circle. If I jump over to f of 4, and I look at my graph, there's only 1 point marked with a x coordinate of 4. And the only point marked with that x value has an open circle. There is no point on the graph marked that has 4 comma some number with a closed circle. This is a DNE. So function values are parts A, B, and C. And then the limit values. The limit values, so for the limit as x approaches some number from the left-hand side, which are kind of the D's and E's, this is just going to be the y-coordinate of the point. How do I say this? It's the y-coordinate of the point that gosh, I can't spell, that the graph gets closer to, or connects to, how about connects to, for values to the left of that number. How about to the on the left side? Trying to use words here and it's not really coming out so nicely. And let me do this with a plus. The limit as x approaches some number with a plus is going to be the y-coordinate. Could be the y-coordinate of a closed circle, could be the y-coordinate of a closed circle, and then of the point the graph connects to on the right side. And I'll show you that with my problem, not to spoil all of your homework, but this should go real quick. So for my problem 2, part A, B, and C, it gives me a graph and wants me to call out and find some just function values, not calculus values. So for f of 1, I go to find, looking for points that have x coordinates of 1, and there's 2 points. There's the point 1, -1, and the point 1, 1. So those are the points that have x coordinates of 1. The point 1, 1 has an open circle. I'm going to discard it. The point 1, -1 has a closed circle. My f of 1 for problem 2 is going to be -1. To do f of -1, I look for points that have x coordinates of -1. And there's only one point on my graph that has an x coordinate of -1. It's the point -1, 1. There's no other point with an x coordinate -1 marked. Since the point there is marked with an open circle, there is no point that has a x coordinate of -1 marked with a closed circle, then that means the function doesn't exist there. Lastly, to do f of 4, I look for the points on the graph marked with an x coordinate of 4. There's 2 of them, one with an open circle, one with a closed circle. The answer for the function value is going to be the point with the closed circle, the y coordinate of the point with the closed circle, which is -5. Now for the calculus parts. Left-hand limits at 1, right-hand limit at 1, two-sided limit at 1. To do the left-sided limit at 1, I'm looking at the portion of the graph that connects to the point that has a x coordinate of 1 onto the left side. So there's two halves. There's a part of the graph that reaches the point that has x equal 1 to the left of it, and that's what's called for in part A. The portion of the graph that's called for in part D, should I say, is this portion of the graph. It's the portion of the graph that's directly to the left of the points that have, to the left of this point right here, and the y coordinate of that point is -1. So what I'm doing for is I'm looking for the y coordinate of the point that the graph connects to, and that's going to be this y coordinate right here. To the left of 1, the y coordinate that the graph connects to is -1. For the part E, I'm blocking out this part of the graph, and I'm looking at this portion right here. I'm looking at, if I draw like kind of a backwards arrow, the point that the graph connects to the graph to the right of 1. So the graph to the right of x equal 1 is shown on the screen right now, and that open circle is the kind of that's the point that has the x that I'm looking for, and I want the y. The y is going to be 1. So I kind of stumbled through that a little bit. So we kind of have a left half and a right half, and this is for the minus limit, because that is to the left of 1, and this point is for the plus limit, at x equal 1, because that portion of the graph is to the right of 1. It's always going to be the y coordinate of either a closed or an open circle that has that x value, and it's just a matter of knowing which of the points, if there's multiple points, you need. And as we do more of these, it should get more obvious. For the part F's, if the left-hand limit and the right-hand limit are the same number, then the two-sided limit is that number. Here, the left-hand limit is -1, the right-hand limit is +1. If the left and the right-hand limit aren't the same, then it's a do not exist. Let's look at 4 now. And first I'm going to do the left-hand limit at 4. And this is the portion of the graph that I'm looking at for it. I'm looking to the left of 4 and finding the point that the portion of the graph to the left of 4 connects to, and it connects to the point 4, 4. The y coordinate is 4. The left-hand limit at 4 is going to be the y coordinate of that open circle, which is 4. The right-hand limit is going to be from this portion of the graph. This is the portion of the graph to the right of 4. So I look to the left of 4, to the right of 4. The portion of the graph to the left of 4 connects at the point 4, 4. The portion of the graph to the right of 4 also connects at the point 4, 4. The right-hand limit is also 4. The limit does not have to be an open circle or a closed circle. The function value has to be a closed circle. The limit can be the y value of either an open or a closed circle. And in this case, both the left and the right-hand limit are the same number. So the two-sided limit in part I is that number. Let me show your problem 3 on the screen so you can take a shot at doing it. And if you can do it without me doing problem 4, then so be it. You can do it and check your answers. I'm going to move on to problem 4. And first do my function values. So first I want to find f of 0. 0 in terms of x is the y-axis. I see 2 points, 0, 4 and 0, negative 5, marked with x coordinates of 0. I want the y coordinate from the solid dot, so my answer to part A, f of 0 is going to be negative 5. For part B, I go to look for the points that have x coordinates of 4. There's the point 4, 11 and 4, negative 10. I want the point that has a solid dot, and I want its y, so it's going to be negative 10. And then lastly, f of 15, there's only one point marked with a 15 as its x. It has an open circle. There's no point that has a closed circle with an x of 15. So this is going to be a DNE. Now I'm going to look at the left-hand limits and the right-hand limits. First at 4, then at 0. So for the left-hand limit at 4, this is the portion of the graph that I'm looking at. I'm looking at the portion to the left of 4, and the portion of the graph to the left of 4 ends at the point 4, 11. So the left-hand limit at 4, the limit with a little minus sign, is going to be 11. The portion of the graph to the right of 4 also connects at the point 4, 11. So the right-hand limit is also going to be the y-coordinate of that point, which is 11. Limits can be y values of open circles, they can be y values of closed circles. It doesn't matter the nature of the circle. Since the left-hand limit and the right-hand limit are the same, the two-side limit is that number. Now I'll move on and do the left-hand limit at 0, the right-hand limit at 0, and the two-sided limit at 0. The left-hand limit at 0, the portion of the graph to the left of the points that have x, of the point that has an x coordinate of 0, runs into the graph at the point 0, 4. So the left-hand limit is the y-coordinate of the point that the portion of the graph to the left of that x equal to 0 runs into, and that's 4. So the left-hand limit is going to be 4. The right-hand limit is from this portion of the graph. The portion of the graph to the right of 0, where is its x connected, or which point does it connect to? What points with the x coordinate of 0? It connects to the point 0, negative 5. The right-hand limit is going to be negative 5. Here, the left and the right-hand limits don't match up, so the two-sided limit does not exist. Let me show 5 on the screen so you maybe can give it a go. If you don't need to watch me do 6, don't watch me do 6. It's not necessary to watch every minute of every video. I'll move on to 6. First, it wants me to do some function values. F of 5, I see 2 points that have x coordinates of 5. I want not the one with the open circle, I want the one with the closed circle, and I want its y. The answer to f of 5 is going to be negative 2. For f of negative 3, there's 2 points, the point negative 3, 8, and the point negative 3, negative 5 that have x coordinates of negative 3. I want the y coordinate of the point that has the solid circle, which is negative 5. And then I'm asked to do f of 4, and the only point that's marked with an x coordinate of 4 is the point 4, 16. It's marked with an open circle. There's no point marked that has a closed circle with an x coordinate of 4. So this is a DNE. Now I'm going to do my limits. My limits, left-hand limit at negative 3, right-hand limit at negative 3, two-sided limit at negative 3. My left-hand limit is going to be the y coordinate of the point that I just marked. My right-hand limit is going to be the y-coordinate of the point that I just kind of highlighted. So this is the portion of the graph to the left of -3, the portion of the graph to the right of -3. Limits are always y values. The y value of the points that the graph to the left of -3 connects to is y equal to 8. So the left-hand limit is going to be 8. The y value that the portion of the graph to the right of -3 connects to is the point is -5, because that's the point -3, -5. So the right-hand limit is going to be -5. And for the two-sided limit, where I don't have the plus sign or I don't have the minus sign, since the left and the right-hand limit don't match up, that limit doesn't exist. For G, H, and I, it's the left-hand limit at 5, the right-hand limit at 5, the two-sided limit at 5. And these are all going to be the same number. The portion of the graph to the left of 5 attaches to the point 527. So the left-hand limit is going to be 27. The portion of the graph to the right of 5 also connects to the point 527. So the right-hand limit at 5 is also going to be 27. And that makes the two-sided limit the same. The two-sided limit is either does not exist if the left and the right-hand limit aren't the same, or it is what the left and the right-hand limit are. So this isn't that hard. Hopefully I did a good enough job that I made it not ridiculous. The next limits are at infinities. And that's not a two-sided limit at infinity because there's only one side. It's not infinity only has one side. There's no number to the right of positive infinity. Similarly, there's no number to the left of negative infinity. This is your problem 7. I'll do problem 8, and maybe my doing problem 8 will motivate you to do problem 7. I'm auto-focusing because I'm not sure how clear this is looking right now. So to do the right-hand limit at infinity, I just go to the right edge of the graph, and the right edge of the graph is, this is my right edge of my graph. This is where infinity would be if I get up far enough. And anytime I draw a dashed horizontal line, the y-coordinate of that horizontal line, in this case -5, is going to be what the limit at the appropriate infinity is. Since to the right of the origin, the graph is heading toward this bottom dashed line, the limit as I go to positive infinity is the -5, the coordinate of that. For negative infinity, because negative infinity is to the left of the origin, if I want to find the limit at negative infinity, I just go to the portion of the graph that's to the left of the origin, and if it's tracking towards a dashed line, the y-coordinate of that dashed line is the limit as I go to negative infinity. So this dashed line has a y-coordinate of 5. The limit as I go to negative infinity is going to be positive 5. Because the left-hand side of the graph goes to the line y equals to 5. The right-hand side of the graph goes to the line y equals -5 for what that's worth. So your problem 7 is kind of flip-flopped, but it should work real similarly. Your problem 9, both the left and the right side of the graph go to the same dashed line. Both the limit at negative infinity and positive infinity will be the same number. For my problem, I don't know. I don't have a problem 10. I don't know what happened to problem 10. So let's just do problem 11 together. The limit as x approaches positive infinity, this is the positive infinity side. Since there's a dashed line, the limit's going to be the y-coordinate of that dashed line that this portion of the graph is buttoned up against, and that's going to be 5. I guess I can write it nicer. Similarly, because negative infinity is to the left of the origin, and this graph to the left of the origin butts up against the same horizontal line, the limit as x goes to negative infinity is the same y for that same line. It's y equal to 5. So for this one, the limit as x approaches negative infinity, still that same 5. There's only one horizontal line that this line is tracking to, so the limits are the same. The next few limits, the graph doesn't flatten out, and it's a limit at infinity. when a graph doesn't flatten out and you're finding a limit at infinity, the limit's either going to be positive infinity if it's getting higher, negative infinity if it's getting lower. So when I go to do my first limit, my limit as I go to positive infinity is on to the right of the origin. Negative infinity is to the left of the origin. To the right of the origin, my graph is going down. It's going to the bottom of the y-axis, and that's the negative y direction. My limit as x goes to positive infinity, cross the origin, the graph goes down, and it goes down to the bottom of the y-axis, which has a y-coordinate of negative infinity. So I would say the limit as x goes to positive infinity is the y-coordinate of where that arrow is pointing, which is negative infinity. And then for the next one, the limit as x approaches negative infinity, I look to the left of the origin. To the left of the origin, the graph is not stabilizing. If the graph was going to stabilize and the limit was going to be a number, I'd draw in some dotted lines. Since this graph isn't stabilizing, the limit has to be an infinity. And because to the left of the origin, the graph is getting higher, and y's, as I get higher, they're positive, I'll say the limit as we go to negative infinity is this positive infinity. I think your problem 11 is the same. Maybe I flip-flopped it. No, it's about the same. 13 is another limit at infinity, but the graph goes in the same direction on either side of the origin. Similarly, my problem 14. If I look to the left of the origin, this is going to be for the limit as x approaches negative infinity, and to the right of the origin, it's going to be for the limit as x approaches positive infinity. Well, to the left of the origin, the graph is pointing down. The limit's not going to exist because it's not going towards a dashed horizontal line on either the limit to positive or negative infinity. Both of my limits, because both sides to the left of the origin and to the right of the origin, the graph is going down. Both sides, the limit's going to be negative infinity because they're both pointing towards the bottom of the y-axis as opposed to the top. Whereas in your problem 13, to the left of the y-axis or to the left of the origin and to the right of the origin, both of your sides are going up. Both of your limits are going to be the same. You just have to know what they are. The rest of the section is filling in tables to do left-hand limits, right-hand limits, and two-sided limits. And no way I want to do a single table by hand. So for all the tables, I'm just going to use the table feature on my calculator, or the ability of my calculator to enter tables. So for 15, which is going to be your problem that I'm going to skip over, you need to fill in the table and figure out a left limit and a right limit and a two-sided limit if there is a two-sided limit. So for 16, I'm going to put the function 2x minus 3 in my y1. And because the limits is such a small number, I'm just going to go zoom standard. I don't need to have my calculator getting huge values. If I look at 4, if I count over 1, 2, 3, 4, the sides of the graph are connected on 4. The left side and the right side are the same. The two-sided limits should exist. Two-sided limits don't exist when there's like a jump between the sides. But let me find out these y values real quickly by going second, calc, hitting enter on value. First I'll type 3.5. My first y is 4. Then I'll type 3.9. My second y is 4.8. Then I'll type 3.99. My third y is 4.98. And then I'll type 3.999. And I get 4.998. This to me is convincing enough to say what the left-hand limit is. It looks like as the numbers that I'm putting in are all smaller than 4 but getting closer to 4, the y's seem to be getting closer to 5. I'm going to gamble that the left-hand limit is 5. Now I'm going to do the right-hand limit by plugging values in that are bigger than 4 but getting closer to 4 and writing down their y's. So I'm going to do 4.5 and get 6, 4.1 and get 5.2, 4.01 and get 5.02, and 4.001 and get 5.002. And again, it looks like all these numbers are trending towards the same number. I believe that the right-hand limit is also 5. And because there wasn't a jump or a break in the graph, the left and right-hand limits were going to be the same. And means the two-sided limit is going to be the same. So A, I filled out my table to predict the left-hand limit. B, I filled out my table with numbers bigger than 4 to figure out my right-hand limit. And because the left and the right-hand limit are the same, my two-sided limit for part C is going to be that number. This is your problem 17. And I'll do 18, which should inspire us to do 17. For 18, I'm doing a left and right hand limit at 1. So let me enter this on my calculator because I don't want to do y values by hand. It just seems silly. It just takes too long to do. It's not particularly interesting. So this graph actually is going to have a break at -2. There's a vertical asymptote at -2, but above and below x equal 1, that's about right there. There's not a jump in the graph. The left and the right hand limit are going to be the same number. And let me figure out what they are. So I'm going to put in first numbers smaller than 1, but getting closer to 1. So let me do second calc value, type in 0.5 and get 2.2. And then type in 0.9 and then get 2.03. Should say round to 2 decimals, so I'm not going to write down a million decimals for these. Then 0.99, 2.003 if I want to write it, and 0.999, 2.0003. So I really wanted to get lots of decimals. I could write that into the first non-zero. But clearly, to me, these numbers are getting closer and closer to 2. I believe the left-hand limit is 2. We do the same for the right-hand limit. Type in 1.5 and get 1 point, I'm going to round to 2 decimals, 86. And then 1.1, round to 2 decimals and get 1.97. And then 1.01 and get 1.99. That would round to 2. Let me just not write 2 down, but it's okay if you did because that's what the limit's going to be. And then lastly, 1.001 and getting 1.9997. If you rounded to 2, this would be fine. All of these, if I'm rounding to 2 decimals, eventually are going to round to 2. That's because that's what the right-hand limit is. So left-hand limit 2, right-hand limit 2. That means the two-sided limit is 2. These are funky with the square root, a little bit harder to enter on my calculator, but nevertheless we can do it. So let's do 20 by entering this function in. And to do a fraction on my older version of the TI calculator, I'm going to go parentheses for the numerator, second and square root of x, and then my calculator to do a square root puts a left parentheses in. I need to close the right parentheses. So right now I really just have the square root of x minus 2. When I close out the parentheses, that's how my calculator enters the fractions numerator. I have to put the entire numerator boxed in a parentheses and the entire denominator boxed in a parentheses. And now divided by x minus 4. There's my denominator. I don't really need to see the graph, but I certainly can. Didn't show up so well because the window's not really suited for it. The y's must be really small. The graph is buttoned up against the x-axis. But let's try to get these y's. So first y, second calc value, type in 3.5, and I get, I'm going to just say 0.26, rounded to 2 decimals, and then 3.9, I'm going to say 0.25, rounded to 2 decimals, and then 3.99, I'm going to say 0.25, rounded to 2 decimals, and then 3.999, and I'm going to say 0.25 rounded to 2 decimals. So at 2 decimals, if I'm not carrying more than 2 decimals, even at my second value, all the y's are the same. I believe that's what the limit's going to be. And it's actually, when we do algebra, we're going to get 1/4 for that. We're going to get a fraction answer. Let me do some more for the right-hand limit. 4.5 gives me 0.24 rounded to 2 decimals. 4.1 gives me 0.25 if I round that 248 to 2 decimals. 4.01, if I round to 2 decimals, 0.249 rounds to 0.25. And 4.001, if I round to 2 decimals, again 0.25. So if I'm just rounding to 2 decimals, eventually I get to the limit pretty quickly. Both the left and the right-hand limit are 0.25, which makes the two-sided limit 0.25. Your problem 19 is exactly that, except I think it's going to be 0.33, but I'm not sure. Now we need to do a couple limits at infinity on our calculator. And to do a limit at infinity, not only do I need to enter the function in my y1 properly, putting the numerator in a parentheses, the denominator in a parentheses, I also have to expand my x max. So when I go to do my problem 22, in my y1, I'm going to enter 6x squared plus 2x plus 5 divided by, and then 3x squared plus 4x minus 4. I need the entire numerator and denominator in a parentheses. If you have a newer calculator than mine, you can probably enter this as a fraction and make it look like that and not need the parentheses. An important thing for this one is the window. And my window, it needs to at least have an x max of 1,000,000. I'm just going to make it 2,000,000 to be safe. For these problems, you're going to get an error when you're trying to find your table if you try to put in a number bigger than the x max allows. If you just kept the negative 10 to 10 table, you'd get errors all along. So real quickly now, y equals clear parentheses 6x squared plus 2x plus 5 divided by parentheses 3x squared plus 4x minus 4. Hit my window button. I don't really care much about the mins, but I need the max to be at least 1,000,000. Don't really, well, you could see now this graph is flattening out. The limit's going to exist. It's going to be whatever the y coordinate of that line is. Let me get some tables now. So second table, plug in 100. I'm just going to round to 2 decimals. To 2 decimals, I get 1.98. And then plug in 1,000. To 2 decimals, I already get 2. 1.999 rounds to 2. And then 1,000,000. You get 1 in all those 9s. That rounds to 2 if I'm rounding to 2 decimals. And then 1, 1, 2, 3, 4, 5, 6. That also rounds to 2. I took the time to type these numbers up, but I don't need that much accuracy. The only reason I'm doing the table is to figure out what the limit is. Once from my table I have an idea of what the limit is, I don't really need to fill in the whole table, and my table doesn't need to be ridiculously accurate. The rounding is just, this is just so you can figure out what the limit is. And if you choose to carry all the decimals like I wrote down here, or if you choose to round to 2 decimals, as long as you can predict what the limit is, doesn't really matter how many decimals you carry. This is your problem 23. I'll do 24 on my calculator real quickly. So for 24, I'm going to enter, do y equals and do parentheses 2x squared plus 2x minus 5 divided by 3x up arrow 4 minus 5x plus 2. And this graph is actually going to flatten out on the y-axis, on the x-axis should I say. Let me plug 100 in. second calc value, and I might get something with an E. Yes, I do. So my calculator gave me this. It gave me 6.7317 e to the negative 5. This is my calculator's version of scientific notation. What it tells me to do is to take this decimal and move it 1, 2, 3, 4, 5 places to the left. This is what my calculator gives me. It gives me 1, 2, 3, 4 zeros and then 67137. Rounded to 2 decimals, that's just 0, because this is, to the second decimal, it's 0.00. When I plug in 1,000, it gives me 6.6733 e to the negative 7. If I wanted to make that into a decimal and get rid of that e, I'd have to drag the decimal 7 places to the left and then fill in with zeros. The decimal version of this is going to have 6 zeros and then 6673. Rounded to 2 decimals, you'd get 0.00. And then, just to save time, because we're already at 36 minutes, this one's going to round to 0 to 2 decimals. So the limit I'm going to say is going to be 0. One more. It's a little longer than I want to make my videos, but this is the last problem for the section. So I'm going to do problem 26. I'm going to enter the function parentheses 2x up arrow 7 plus 2x up arrow cubed minus 5 divided by parentheses 3x up arrow 4 minus 5x. Numerator goes in its own parentheses, denominator goes in its own parentheses. This graph is not going to flatten out, but let me show you real quickly how we can find our limit. So second calc value, type 100 in. When I type 100 in, I get 666,667. I don't need to carry the decimals. When I plug 1,000 in, I get, let me see here, 1, 2, 600, oh my god, devilish here, 666,666,667 if I'm not carrying any decimals. And when I plug 1,000 in, I get this. It probably gives me 10,000 in. It probably gives me an E. When I plug, no, yeah, it did. It says E to the 11th, and it's E to the positive 11. So it gives me 6.6667. And in this E notation, if the E, the number following the E is a negative number, you need to move the decimal to the left to get rid of the E. If the number following the E is a positive, you need to move the number to the right. So to get this out of decimal notation, out of E notation, 4, 5, 6, 7, 8, 9. I need to move the decimal 11 to the right. And anytime I pass all my numbers, I need to add zeros. And so this down here is the decimal non-E version of the answer. The important thing is that these y's aren't stabilizing, and they're getting progressively bigger. They're getting positive bigger. This limit's going to be positive infinity. So that's everything for section 1.1. Section 1.2 is going to get into just normal algebra. We're going to find limits without tables, without graphs, using algebra. And I like it better. So let me pause the video and we'll move on and do section 1.2 when you get ready to do it.